Okay, 3, 2, 1. 3, 2, 1.
What?
3, 2, 1, go. In order to figure out what the distance from the upper commons to the lower commons is, we dropped the sponge off the upper commons and timed the amount of time it took to fall to the ground. Then, after averaging the times, we plugged it into a kinematic equation, which gave us delta x, or the distance from the ground to the upper commons in meters. We also measured the distance with a measuring tape, which we then used to prove that our math was correct. This is the math we did.
6.39. Okay, 6.61.
Perfect.
What are you doing right now, James?
I'm making sure the length of the string doesn't change in between trials here.
Oh, okay, that's cool. Okay. I'm good. 6.42. 6.53.
Okay.
Okay, last one. 1, 2, 3. 6.87.
This experiment proves that mass doesn't change the period of a pendulum. First, we timed how long it took our pendulum to travel 3 periods. We chose 3 periods because it gave us enough time to accurately measure a period's length. When we used a 500-gram mass, the amount of time for 3 periods was 6.39 seconds and 6.62 seconds. When averaged, this gives us a time of 6.49 seconds. Then, we used a 100-gram mass. Despite the change of 400 grams, the time it took for 3 periods was 6.42 seconds, 6.53 seconds, and 6.87 seconds. The average here was 6.6 seconds. When compared with the first time of 6.49 seconds, this proves that with account for human error, the mass of pendulum doesn't affect its period length. 3, 2, 1, go. In order to explain Newton's first law, we spun a mass on the end of a string in a circle. Once we let go of the string, the mass flew tangentially to the circle. Because it was set in motion, when the force was taken away, it wanted to keep going in the way the force was applied. That explains why the mass flew tangentially to the circle, because it went in the same direction as the force that used to be applied to it. This proves Newton's first law: an object in motion stays in motion unless acted upon by an outside force.